Hello, Pedro here, and this next Dash package release, the focus will be on didactic assets. These assets are not supposed to be building blocks or part of a setup, but they are supposed to be a visual aid, an interactive toy, part of a presentation about educational topics. As you can see, vector and matrix there in the network view. So this is going to be about linear algebra. The reason I've chosen this is because, of course, I was very happy when I finally understood better some of these topics and allowed me to set up things and express things the way I wanted, and having a little bit of less of a frustration time trying to be creative in this field. And given that this allows us to define and set up geometric relationships, this is very rewarding over time because this keeps popping up in rigging, in procedural modeling, procedural animation. So it's well worth to understand them. Now, I find also sometimes some of these topics I have a little bit a harder time making the point across to someone that doesn't know anything about them. And so here it's an attempt of making something that is a little bit in between a theoretical presentation and a practical example, to try to see if this helps people to understand better and grasp the concepts right off the bat, and also test their limits, because this is interactive. They can try to break things and see, okay, what happens if I do this or that, which is also helpful sometimes when trying to define a concept. All right, so I'm going to do a quick rundown first on the vectors and then on the matrices. But if you have suggestions for other topics that you think would be very interesting to have such kind of assets, let me know. Okay, so I'm going to start here with the vector components. For all of these assets, if you want to have control in the viewport, you need to click on Create Interactive Geo. This will create some points or lines, and then a KineFX rig pose that if you select and you press Enter in the viewport, you'll have points that you can click and drag and control the data interactively. You can see how the coordinates update as I move this head point of the vector around. To reset that, go to the KineFX rig pose and control middle mouse button the parameter, and the influence of the rig pose is gone. So what is this asset about? This asset is about position vectors, which are, foundation of all we're going to have to deal with. The P attribute, the normal attribute, etc. And so what is a position vector? Well, it's a vector that has the tail point implicitly at the origin. So we have a vector defined by a tail position and the head position, and we only need to define the head position because the tail position is at 0, 0, 0. So as I move this around, this head point alone defines my vector. Another way to think about how vectors are constructed is to consider the coordinate system where they are included. So if I click here on components, we can see that the coordinates 1.5, 1, and 0.5 can be multiplied with the appropriate unit vector of the space that they exist, and adding those vectors together arrives to that position. So I have this unit vector for the x coordinate. If I multiply it, if I scale it by 1.5, I get this. Then if I scale this y axis by 1 and I add to the end of this vector, I get this. And then if I get this unit vector for z and I scale it by 0.5 and I add to the end of my addition here, I'm going to arrive to my coordinate. So this is another way of seeing how the coordinate system where the vector exists builds up to its location. Now, we can also have the issues that's, well, what if my tail position is not at the origin? What if I want to create a geometric relationship between two positions? So if I come here to the KineFX rig pose and I move the tail point away from the origin, you now get this orange vector for the head point and this blue vector for the tail point. And then between them, there's this purple vector, a vector that goes from the tail to the head. So how can I have its coordinates when it has 2 points? It's existing between 2 points. Well, I need to subtract to the head point, the end of the vector, the start of the vector. So there's this tail point here, and to subtract it, I flip it around and I add it to the end of my add vector. So I can see that by clicking here in local data. I have this copy of my tail position. it's flipped around and added to the end of my head position, and it arrives at this position here, which when connected with the origin gives me a vector that is basically equal in length and direction than the vector that goes from t to h, but is now defined by a single coordinate of its add value where the tail is at the origin. So now this is how you create a vector that you can handle, you can manipulate, you can get information from between two positions that are not at the origin. So in this case, I had to remove the context. We can say that this is the position of the head point in the context of the tail position. Sometimes you have to add back this context. Here I had to remove it, so I had to subtract the tail position to my head position, but there can be situations where you have to add this back. So let's say if I normalize, let's say I normalize this vector here. To normalize means to make a vector of length 1. And if I click here, normalize, there's the normalize function, but you can also divide the vector by its own length, what I've done in here. And so I've normalized the vector by its own length, and it came up to here. Now, how do I get my head position to go into a position that the shadow copy mimics the vector? Well, I need to add back the context. So to this th vector, I'm going to add a copy of my tail position, and my head position is then going to arrive there. So this is the takeaway here is that sometimes you have data that has a context, and you need to be aware of it because you might need to remove it or then later on add it back. Not being aware of this or ignoring this can lead to a lot of frustration because you say, well, but I have the data for those points or for those normals or whatever, but as I do the operation on them, things don't work out the way I wanted. Well, be aware that you're working with the data in the appropriate context. All right, so I have a few other things in here. I have the button to swap the tail and the head position. So of course, this will produce the opposite vector. And there's some buttons here to just, noisily animate the tail and the head position. That's all. Next, we can go into the dot product. So the dot product is a way of basically getting a projection of one vector onto another. And it gives so many things, this operation, that I'm just going to present a few of them. But so basically, it's something, is an operation that is going to be very sensible to the angle between the two vectors. As you can see in here, if I animate the vector b, you can see the dot product value to update, and it goes from positive to negative and then back to positive. So it goes negative range, positive range, that's it. And that can be visualized further on here with the display helper geo. And you can see that this is the negative range and this is the positive range. And even though the vector is rotating around, this range is actually very linear because it's according to the other vector. So the other thing is that the scale of the vectors also changes. So right now I have these two, this is like 1.2 and this is like 0.8. But if I change, let's say I'm going to put this here, and if I change the scale of the vectors, you can see that the dot product value increases as well. If I change this one, if I change this one, right? So according to the length of the vectors influence the result of the dot product as well. The only time that this is not the case is when the vectors are at 90 degrees, because the dot product is 0. So regardless of the length, so you can see here, as this vector at 90 degrees rotates about the other vector, it's always 0. It doesn't change. But also, if I change the length of each of them, it doesn't change anything, right? Because they are at 90 degrees. The dot product is 0, so the scale doesn't matter at all. Now, when we normalize one of the vectors, we can get an interesting thing like the projection of one onto the other. So if I normalize A, meaning I'm going to make vector A have a length of 1 unit, now I'll have the projection of B, the dot product will be equal to the coordinate of B along the normalized A. So if I animate this a little bit, you can see that this value, this dot product value of 0.561, if multiplied or if this vector A is scaled by that dot product, we're going to get this projection vector here. So this vector, as you can see by the dotted lines, is the projection of B along A. And of course, if the dot product is negative, the projection is going to be pointing in the opposite direction of A. So this value of minus 0.575, when used to scale A, is going to give me this vector here. When we have the projection, if we subtract it to our initial vector, so if I subtract it here to B, we get the rejection. And so in the end, this gives us two vectors that are like the decomposition of one vector according to the direction of the other vector, and allows us to basically do operations on each of the components separately and maybe add them together again. Because of course, if I do projection plus rejection, what I get is B again, right? But this is like, splitting my vector into a set of coordinates that are not the main coordinates. Right, so the same thing if I normalize just B, right? So I normalize A like this, if I normalize B like this, then now I get A projected onto B. So here on the negative side of things, and then here on the positive range. Now, if I normalize both of them, A and B, what I get is the cosine of the angle. And this has a clear range of -1 to 1, right? This is like the same thing that is used in lighting fall off, the incidence. So it's a linear gradient. So we have the vectors having this angle, and the dot product gives me the cosine of the angle. This is useful because a lot of times in some calculations, you actually don't want the angle. You just want the cosine of the angle. So for example, in this case of the light fall off incidence, you want to, let's say, control the intensity of how much light is affecting a surface according to the angle of the normal. And that's all you need. That is that linear fall off of the cosine of the angle. You don't actually need the actual angle. But there, of course, if you use the arc cosine function, you can get the in radians, you can get the angle between the two vectors. All right, so now let's go into the cross product. And the cross product is something that returns a vector that is perpendicular to both input vectors. So I have A and B, and then I have this vector C that is perpendicular to both of them. And if I animate vector B in here, you can see how that changes. So when I rotate vector B about the cross product, you can see the axis doesn't change. The direction, or let's say the line of the vector, doesn't change. What it changes its magnitude, and if indeed it will point downwards, and then it will point upwards. And why does it point upwards or downwards? Well, this is because of it's using the right hand rule, right? So if I'm doing cross from A to B, if I put my right hand in here and I close my hand as I rotate A to B, my thumb will be pointing up. So there's a visualization of that in here, where basically this is what happens. As I close my hand, as I would be rotating A to B, my thumb, my right hand thumb, points up, and that's why the cross product should be pointing to. Now, if I animate this, or let's say I come here and I create interactive geometry, and I move this around, you can see as I cross this, the shortest arc between A and B is on this side. And now, if I would close my hand, my thumb would be pointing this way. So this is why it's called the right hand rule, because it's something that you can easily just use your hand to think about it. Now there's some extra information here in this parallelogram. The area of this parallelogram is equal to the length of the cross product. So as I animate this, you can see that this diminishes as they become aligned, and the area of this parallelogram is also diminishing. So they do match in value, the length of this vector and the area of the parallelogram. Now, if I normalize both inputs, meaning make A and B have length 1, what happens is that the area of this parallelogram, or the length of the cross product, will be equal to the sine of the angle. So with the dot product, we got the cosine of the angle. With the cross product, we get the sine of the angle. And so here you can see that using the function arc cosine, we can also get the angle between the two vectors. So one thing that I decided to include, because I thought maybe it would be interesting, is the double cross product. So what is the double cross product? Well, we've done already, the cross product between A and B. But what if we do the cross product again between the C and A? So if I animate this, this is what you get. So cross product AB gives me C. Cross product CA gives me this vector here. And these three are all perpendicular among each other. If I normalize both inputs and outputs, what we can do is a matrix using A and both of the cross products, because now they are all orthonormal, meaning they are perpendicular among each other, and they're also normalized. They have length 1. And this is our first, let's say, I guess, our first matrix using the double cross product. So one cross product and another cross product following up that one. And if I normalize everything, then, well, basically that's just basically a nice rotation matrix. I can just grab this in here, and this is like a LookAt function. And if I animate this, you can see the green hand showing the cross product between A and B, and then the red hand showing the cross product between C and A. So the thumb, if you check where the thumb is pointing in the direction of this red vector. All right, so that's it for vectors. Next, I'm going to look into matrices. So matrix components hopefully will make the point across about what are the values present in the 4x4 and 3x3 matrices. By 4x4, meaning we have 1, 2, 3, 4 values. By 1, 2, 3, 4 values, and same for the 3x3 matrix, you have 1, 2, 3 by 1, 2, 3 values, right? What these values aren't is a mapping of things like a storage of transforms, like the transform solve, right? Where you have this grid of values in here, and this row is the translate, this row is the rotate, this one is the scale, this one is the shear. These have nothing to do with each other, right? What you're defining here with the matrix is the definition of a coordinate system. So we have the unit vectors of that coordinate system, and by deforming those and then mapping positions into that system, we can enact transformations, just like the transform solve, scale, shear, rotate, translate, etc. But the values themselves are not a record of those transforms. So let's look into a practical example here. First, let's focus on the 3x3 matrix. So in the 3x3 matrix, we have 3 vectors. In the first row, we have this red vector. In the second row, we have this green vector. And in the last row, we have this blue vector. And what these are defining is the basis vectors of the coordinate system. I can manipulate them, right? So if I come here to the pig head and I create interactive geometry, if I go to the KineFX repos and I pull off this red vector here, now what I'm doing is changing the length of the red vector, and by multiplying the pig head by this space, now I'm scaling the pig head on the x-axis by 2. So deforming the space definition and then transforming the mapped positions. So this is scaling. If I pull the green vector up and down, you see that I'm doing scaling along the y-axis, and same for the z-axis, right? If I expand it, if I extend it or compress it, I'll be doing some scaling. We can also look into the representation of the coordinate axis and how they change as I do this. So for example, here, if I pull the red up, you see that the coordinates expand. If I pull the red down, the coordinates compress. So the coordinates in this space are more compressed on the x-axis that they are on the other axis. Right, let me reset this. The other thing you can do with the 3x3, so this was a demonstration of scaling. And if I do, let's say, an animate here the scale, and I just play the timeline, you can see that these 3 diagonal values animate, but not the other ones, right? So the other thing I can do here is shearing, and shearing I can do instead of pulling the y-axis up and down like this, I'm gonna move it parallel to the ground. And now this is doing a shearing where basically the coordinate axes are no longer perpendicular with each other, right? So this is shearing, and if I reset this and come here and animate the shear, you can see that these vectors are being transformed along their perpendicular direction. So this diagonal row is actually not changing, only the other values are changing. Okay, so the last transform that the 3x3 can do is a rotation. So I could manually try to do that by, posing each one of these vectors. Let's say I'm going to try to do a rotation here. It's going to look awful. Well, let's say, okay, let's say I perform a rotation here, but this is very imperfect. But by manipulating the components of the space to try to have them all consistently rotate like this, and then mapping the pig head, I rotated the pig head. What is easier to do, though, is, let me reset this, is to pick up the parent transform, the translate, press R to rotate, and just rotate them all at the same time. And what you can see here is that they are all transformed at the same time. Now, it's kind of hard when you check the geometry spreadsheet to make sense of these values, right? Because especially when you introduce rotation, all those values just kind of look random. So if you come here to the geometry spreadsheet, this is the matrix that we're looking in here. And I have here a representation. If you turn this on, right, this is something that is supposed to match what you have here in the geometry spreadsheet, right? So let me come in here and make this full screen. And so for the 3x3 matrix, it's going to look like this. So it's going to be flattened by row. So the first row, second row, third row. And for the 4x4, you're going to have the first row, the second row. See, this is vector 4, right? So the rows are slightly bigger. And it's going to look like this, right? So it's not very meaningful when we start to introduce rotation to look much at the spreadsheet, because these values just become, they look kind of random, to be honest. If you have like this is not very meaningful. Still, it's good that you know what each, at least kind of the regions of the values, because it will still allow you to kind of debug, like immediately look at some values in a matrix and maybe something is off. So let's introduce the translation here, for example. So if I come here and I'm going to turn off the rotation animation, and I'm going to turn off the spreadsheet layout, and I'm going to move the pig head away from the origin. Now, this cannot be performed with the 3x3. We need to go with the 4x4. So I click here on the translate, I press T to move, and I move it away. And now you can see that this is the part of the matrix that changes. Now, let's say you were expecting to have a matrix with some translation, and this here is all zeroed out, right? Let's say this part of your matrix here is all zeroed out. Well, then there you have a problem, right? Something is wrong. And even if you don't have any transformation, let me reset this. If you're doing something wrong, sometimes the matrix is all zeros, and that's also wrong, because usually an identity matrix should have a ones in here, right? So if this is all zero, you're doing something wrong, and some code is introducing some issues that is zeroing out all of your matrix, or you're importing your matrix wrong, something like that. So it's not very meaningful to look at the spreadsheet at the values like this. The rows and columns, it's a little bit better, but it still can provide some debug capabilities. Let me turn this off. And let's look at something that is akin to something that I've shown before. Let's say that I'm going to rotate, and yeah, rotation only, I guess it's fine. Or well, let's do some scaling. Yeah, let's have some scaling. We have this here, this coordinate, minus 0.8, 0.5, and 0.3. And this is the result of it being transformed by the matrix. So if I come here and I increase the length of this vector, the transformed value will be this, while my input value was this, right? And we can check the components as we checked before. So if I come here and I check local components, what are these components? Are basically versions of my unit vectors, my basis vectors that define my 3D space, scaled by the coordinates of the vector. So if I multiply this unit vector by minus 0.8, I'm going to have this component here. If I multiply my y unit vector by 0.5, I'm going to have this component here. And if I multiply the z-axis by my coordinate here, 0.3, I'm going to have this small 0.3 copy in here. Now, as I manipulate these basis vectors, you can see that the copies also get deformed. So if I shear this one is going to be shearing. If I increase its length, it's also going to be longer. If I make it shorter, the copy is also going to reflect that, right? So hopefully this, like I said, makes the point across that what we're doing here is defining is manipulating the definition of a 3D space and then deforming positions by mapping into that 3D space. If I want to, let's say, show the local components and the world components, I can do this, let's say, and then come here to the asset and click on world components. And so we have here the local components on the matrix. And then we have here the world components along our usual scene axis, so x coordinate, y, z. So these components are relative to the first row. These components are relative to the multiplication result between the vector and matrix. Right, so maybe this is a little bit too convoluted, but I thought it was a good inclusion given what I've shown in the vector components. All right, so last thing, I've shown the translate, I've shown everything. The only thing I'm missing to show here is the projective transformation. So let's see here. Projective is not very used. The multiplication operator doesn't even support it, but it's good to know. Like it should be at the 0, 0, 0, 1. If not, maybe you're doing something wrong with your matrix. But if you know how to use those values to transform your geometry, this is the kind of thing that you can get out of it, right? So lines that were parallel are no longer parallel. They have an angle now. Of course, the lines are still lines, so this is still linear, but they are not parallel anymore. So this kind of projective transformation is what you get from like a viewport, a camera, etc. And it can, if you have some functions like NDC and stuff like that, that will use this kind of transformation. Unfortunately, you won't be provided a matrix, which is a shame. But you can see that what lights up is this part in here. And of course, if I change it manually in here, you can also see those things taking place. All right. So last thing before we leave the matrix components is what happens if I invert a matrix. So let's say I have here a translation animation. If I invert the matrix, what should happen is that the opposite action is done. The opposite transformation is done. So before we had the big head being offset up here. Now it's being offset down here. So this is a shadow copy of what was our input matrix, and this is the inverted version now. Same for rotation, right? If I was supposed to be rotating in one direction, now it's going to rotate doing the opposite rotation. And same for scaling. If I was going to scale up, then I'm going to scale down. So this one is scaling up on the x-axis. So the inverted version, actually, sorry, the other way around. this is scaling down on the x-axis, so the inverted version scales up on the x-axis. So this is basically what inversion is about doing the opposite transformation, or changing the definition of the 3D space so it matches that opposite transformation. All right, so that will be it for the matrix component. Next, we have the LookAt, and LookAt is a very recurring operation, something that you can see in action, for example, in orient along curve or copy to points. If you use the n and up attributes on a copy to points, basically you're doing a LookAt. If you don't use an up vector in the copy to points, you're basically doing a dihedral. And so these are quite fundamental notions of inferring a 3x3 rotation matrix from two directions. So I thought it would be interesting to look into them and visualize what they mean. Okay, so to look at, first to look at, we have two directions, A and B, and we have a matrix being created from them. With the LookAt, what you're going to have is that the forward vector, the z-axis, is going to match the first direction. And so if I create interactive geo and I play with the direction of A, you can see that the forward vector of the matrix is going to match it. Now we have a second direction, because just having one direction is not enough to define an orientation. This second direction B is going to control or constrain where is the up vector of the matrix going to be looking at. So there's a projection of this vector into a plane perpendicular to this first direction and then normalized. And so this is what the result of it. So it it's like a roll control. I can define, I have this direction pinned down, but by moving this one around, I can control the roll of the matrix. And I have some helper geometry here and some animation that hopefully will help to make this also more clear. So we have Tommy looking at the soccer ball, and as I animate this, you can see that it tracks the soccer ball, and the up vector now is animated, so you can see that it keeps looking at the soccer ball, but it's rolling about that direction, controlled by the position of the second vector. The hand animation is in here just to demonstrate that this axis here is inferred by the cross product from B to A. And given the right hand rule that we looked at before, this means that this axis should be pointing in that direction. Right? So as you close your hand with your right hand and you put your fingers pointing at B and then you close them to A, your thumb is going to point into this direction. So yeah, hopefully this makes it clear. If we didn't have a second direction, basically it means that this up vector could be in any position around this circle. But by defining that direction, we said, no, it's not here, it's not here, it's not here, it's actually here. Right? And so this can be very important at times to define this up vector to have this strict control. Like you would want, maybe not want to have a character looking sideways, even though they're looking at your target. They're looking funny, like a cute dog. So most of the times you want the up vector to be upright and the person looking with an upright roll. All right, so dihedral. Dihedral is different from the LookAt in the sense that, as you can see, the forward axis is not constrained to the vector A. What's happening here is that this rotation is a difference between the directions of A. So what rotation should I apply to A so that it becomes B in terms of direction, right? Both these operations, the LookAt and the dihedral, though they don't care about the length of the vectors. The only thing they care about is their direction. And so same here, like the dihedral doesn't care if the vector is longer or shorter. So if I come here, it's the same thing. What matters is like, okay, what's the angle from A to B? And that's the rotation you get. So if I animate this, we have here an animation. And as you can see, B is going to be animated and is going to match A. And as it matches A, the animation becomes an identity. So there's no rotation at all. because they both match. So there's no differential rotation. The rotation for A to become B is nothing, right? It's just an identity rotation, do nothing. As B is animated away from A, then the rotation becomes bigger. And you can see as B is rotating about A like that, you get like a sort of a tumbling rotation. There's a helper, this option here, display helper geo, puts a cube in there to kind of see how a cube would be transformed by having A and B animated, and also displays the axis of rotation and the angle between them. So if I would want to make A have the direction of B, I would have to rotate it about this axis and by this amount in angle. So if I play this back, so they match, and then the cube goes around like that, and you have this sort of like tumbling animation. There's no roll control, right, like you have in here. There's a strict roll control, and this is where sometimes, you know, people forget to add when they use the when they use the copy to points. They forget to add an up vector, and then they get weird kind of rotations, because in the dihedral there is no definition of an up vector. It's like the shortest arc between the two directions. And what the copy to points use as the main direction is the z-axis. So if you have if you have something that is pointing like minus into the minus z space, it's going to create weird rotations. Anyways, these are the matrix assets. I hope these you can see useful applications for these, for presentations and for didactic reasons. Let me know if if you have any suggestions. If you spotted anything that is incorrect, maybe I had something wrong in here. And yeah, I had a lot of fun setting up these assets, and I hope they can be of good use. Cheers.